right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. I was in the middle of teaching you guys how to count last time, so let's actually get back to that. See, there we go. Good morning. There's everybody. It doesn't actually get any easier. Like you would think, like you're waking up 8:30, have an 8:30 class every morning, and you're like, you know what? Eventually, it'll be hard at first, like the first couple weeks, and then eventually I'll get into it. Like, it doesn't get easier. Like, how do morning people do this? I don't know. Like, we're more than halfway through the semester, and I don't feel like this gets any easier. I don't know what's going on. Let's talk about counting.
Imagine if we were in person.
I know. I don't know. In person has a different vibe a little bit. But yeah, I don't think it would be fun either way. I don't know. In person has a different energy. However, we are now going to develop some counting energy. So pay attention, grasshoppers. I will teach you how to count. That's what today's class is about. Just going to go through a bunch of counting techniques, counting ideas, principles. We're going to figure some stuff out. I do have some counting examples. I don't think we're going to get to them. But we'll get to them by tomorrow. Today, I'm just going to talk about counting. And also tomorrow I'm going to drop your projects on you. So tomorrow, I'll be putting you guys into groups and giving you the project, putting on some finishing touches. Decided to go a little bit less traditional with it. Hopefully, it's interesting and doable. But let's actually get to counting. What have we done? Well, one thing really. After me teasing you with the Monty Hall problem and all this other stuff, we spoke about something called the multiplication rule, which is a way to count the number of ways that an overall experiment can go if that experiment has several different stages and we know how many ways each stage could happen. So we introduce that in terms of tuples because sometimes you're going to want to be able to count in terms of tuples. Sometimes we want to count with the idea that things have to come in a certain order. There's a certain number of them, and there are certain many options for the first coordinate, certain many options for the second coordinate, etc. And we can think of the entire coordinate as an experiment. How many ways could we create a coordinate? How many ways can we create an experiment, right? Stage one can go this many ways. Stage two can go this many ways. The total number of ways is just you multiply how many options you have for each coordinate. If you want to state that in terms of sets, if you have sets A and B and you're creating a coordinate and you have the first coordinate has to come from the set A, the second coordinate has to come from the set B. How many total types of coordinates can you create? Well, it's the size of A times the size of B, right? You can generalize this. So if you have n coordinates and you have sets A1 through AN, how many possible coordinates can you create? Well, the size of A1 times the size of A2 times the size of A3 all the way up to the size of AN multiplied together. And this can also be stated as an experiment. You can think of creating a coordinate as a whole experiment, maybe. And so you have a certain number, n1 options for the first coordinate, n2 options for the second, n3 all the way up to nm. Then you can create an m tuple by just how many m tuples there are. M as in mom, or Mars, or Margaret. What do they usually use m for? M as in Mars. So then you have n1 times n2 times n3 all the way up to nm. And we did a very simple example there. Okay, so we're going to do more things like that. I'm going to tell you about other counting principles. So besides the multiplication rule, we're going to use the multiplication rule to figure out a lot of things. So the multiplication rule implies the following. Two rules. Okay, one. suppose, so this is like a counting rule that you can do. Suppose A is a set, I was going to say has n elements, is a set with n elements. Then the number of m tuples that can be formed from the elements of A with no restriction. Like, I'm not restricting you from choosing any particular element at any particular time. So this looks like a coordinate A1, A2, dot, 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 all the way up to AM, where the AI all come from A. Is, so how many of them are there? N raised to the M. And why? By multiplication rule. You are creating a coordinate which you can think of as a whole experiment. And there are n choices here. Let's put it, n choices to go here. You again have n choices because I'm not restricting you. So even if you picked an element before, you can pick it again. There's no restriction on the elements you can do. So there's n choices all the way up to n choices. So according to the multiplication rule, and there are here m slots that you can put it in. So the multiplication rule tells you the number of this is n times n times n, da, 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 n m times. So this gives you n to the m, right? So if I'm only looking at, like last time the multiplication rule, we assumed that a different set was in charge of each coordinate. However, if I put one set in charge of every coordinate, and then I give you no restriction, you can pick any element from that set and put in a coordinate, then the number of such coordinates you can create is n to the m. So that's the no restriction. I did do a small example here, very silly example, but it can bring the point home. Example, suppose phone numbers. This isn't true, but suppose phone numbers are 10-digit numbers. With no restriction on the digits. How many possible phone numbers are there? Okay. So one thing you can know, order matters here. Right? Just because two people have the same digits in their phone numbers doesn't mean they have exactly the same phone numbers. So a different rearrangement of digits give a different rearrangement of phone numbers. So a tuple is appropriate. As in not a set. because sets order doesn't matter. Secondly, digits can be repeated. In other words, repetition of numbers are allowed. And again, that means a tuple is appropriate. Not a set. The point is, what I'm trying to tell you is that a phone number can be thought of as a tuple as opposed to a set. You shouldn't think of a phone number as a set of numbers. A phone number is a tuple of numbers. The order matters and numbers can be repeated, and we don't just ignore the repeated numbers. It's a phone number. You need all the numbers. You need 10 numbers. So this means when I start counting phone numbers, I'm going to count them as a tuple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So a 10-digit phone number can be thought of as a 10-digit tuple, and I would think of it as a tuple because of the above reasons. Order matters and repeats are allowed, which means if either one of those are true, I would choose a tuple as opposed to a set to represent the thing I want to count. Now, how many choices? Well, you have 10 choices here because you have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Again, you have 10 here, 10 here, 10 here. And so by the multiplication rule, by the above rule, which is a consequence of the multiplication rule. I could have said by the multiplication rule. The number of phone numbers is 10 to the 10. You multiply all these 10s. That number is huge, by the way. It's not like a little, you know, I want to say all the grains of sand on the planet is like 10 to the 18 or something like that, which is a lot bigger than this number, but it kind of gives you some perspective. So yeah, a lot of possible phone numbers that you can make with 10 digits if you are allowed to, you're no restriction. I could have a phone number with all zeros, 0, 0, 0, 0, 0. Yeah, this is counting all such phone numbers. Yeah. Okay, so that was just a silly example there. However, there are times when we want to do a restriction, an important restriction. Sometimes we do not want to allow repeats. For various situations that we will see later, some examples. And so this leads us to another rule. Let A be a set with n elements. Suppose m is less than or equal to n, so it's some smaller number. Of course, it's so n is some positive integer, and m, as in mom, is some smaller integer. Then, where are we? Then the number of m tuples that can be formed with no repetition from the elements of A. So that's guys that look like this, A1, A2, all the way up to AM. They're M positions where all AI are in A, but all different. So out of a set of n things, I pick m random things to arrange in a coordinate. And I want to pick m different things, m as in mom. And so the number is the following. It's going to be n times n minus 1 times n minus 2 dot 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 n minus m plus 1. So that's the number. And why? Well, by multiplication rule. When you're creating a coordinate, of size m slots here. How many choices do you have to put in the first coordinate? So we have a set A that we want to create coordinates from. In general, you can pick any number you want, any element you want from A. So you have n choices here. However, we're not allowing repeats. So once you pick that guy, you can't pick him again, which means you now only have available n minus 1 choices. You already chose one. Now, when you start to go fill in the third coordinate, who can you pick? You can't pick either of the two people you already picked. So now you only have n minus 2 choices. It's like every time we pick, the set that we're allowed to pick from goes down by the element that we picked. And so this keeps going, right? Now, if you make m choices, you can think of this as you're starting to count, well, no, if I focus on the number that's beside the n here, this is as if I'm starting to count from 0, n minus 0, n minus 1, n minus 2, n minus 3, da, da, da. If I were to go up m times, as in mom, starting to count from 0, it means I will get to the n after n minus m minus 1, right? Because from 0 to m minus 1, those are m things. And so here you have n. Finally, you have n minus m plus 1 when you put the parentheses out. Here you would have n minus m plus 2. And so on. Yeah. So now, when you multiply these guys, that's the number of possible n tuples. Without repetition. This number happens to be a very important number. We will, in fact, give it a special notation and call it a special name. Does anyone recognize this number? I told you it was an important restriction. It therefore leads us to a very important type of number. We denote it by P. and then we write a little nm. So it has n things, you're choosing m of those things, m as in mom, to arrange in a certain order where you're not allowed to pick repeats, right? So this number, n times n minus 1 times n minus 2, dot, 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 multiplying all together to n minus n plus 1, we call it PNM. Other notations. There are a bunch, and it would depend on what calculator you're using, but your calculator should have this number. What are some common, well, I can tell you off the top of my head some of the ones I remember. So PNM would be one, NPM would be one, or NPR would be one. Sometimes people use R. I think people use R because they're tired of saying NM, M as in mom, because I have to say who is the N and who's the M, and no one's going to know what I'm talking about. So they just pick randomly R. NR, NPR, where the R can be replaced by M. Now, at this point, you should sort of be looking at your calculator to see if you can identify this number. If you have a fancy, sophisticated calculator like a TI-84 or TI-89 or something like that, this will be under the math menu. You'd have to look at you'd have to press math, then you'd go to probability, and then in that list, you'll see something that looks like this, NPR. I forgot, do I have my TI-89? I forgot what it looks like on the TI-89. Other calculators will have it straight there. Accidentally clicked something just now. Yeah, other calculators will have something like this there already. So you should make sure you know how to find this on your calculator. And I'll actually ask you guys to do a couple examples later on where actually to plug this into your calculator and find a number. But that's a very important number. And it has a P in it, and we call such a number a permutation. So this number is called a permutation. And why is it called a permutation? Why? The root word permute means to rearrange. When you say you permute something, you're doing a rearrangement of the things, right? Or when you say I created a permutation, it's just that I created a different arrangement of these things. They were arranged one way. I created another permutation, means I just rearranged them another way, right? So to permute means to be rearranged. And so what this is, so what this counts is the number of ways is, maybe I should put that, PNM, how you can think of that number is the number of ways to choose M objects from N objects in a particular order. Without repeats. Right? That's what that number is. So if you want to know, hey, I have 50 books over there. How many ways can I take 10 of those books and arrange them on this shelf? If someone asks that question, what they're asking you to find is P sub 50, 10, right? So example, I didn't plan that example, but since I just said it, I'll write it out. For example, P50, comma 10 is number of ways to choose 10 books from a set of 50 and arrange them on a shelf. For example. Right? So when order matters, that's what you will do. So, hey, there are 20 people over there. I want to randomly pick 3 of those people to be in a certain position on a committee I'm creating. I want a president, a vice president, and a treasurer. How many ways can I do that if there are 20 people? Well, it's P of 20, comma 3, right? So, and why is because the positions have an inherent order in them, right? You expect like the president to be higher than the vice president, to be higher than the treasurer maybe. And so there's a certain order in your head. And so you want to pick things to arrange in terms of that order. You should be looking at a permutation. So that's an example of where that number would come in. So here, there's a special case. P of n, meaning I have n things, and I want to arrange all n things, right? So I have 10 people over there. I want to put all 10 of them in a line where how many different lines can I create with those 10 people, right? So there's going to be a first person, a second person, a third person, a fourth person, right? I need to be able to arrange 10 people. Well, how many possible lines could I create with 10 people if I use all 10? Well, 10 times 9 times 8 times 7 times 6 times 3 times 4 times 3 times 2 times 1. I sure hope I said that correctly. It's early. I'm not used to the 8:30 thing. I know I should be. I just, and just to go back, it would be worse if it's in person. I just want to clear that up. Like, I don't think it would not be. Like, it really would. Because at this point, I can wake up at like 8 or 8:10. Like, if I had to come there in person, I'd have to be up much earlier. It would be worse. But yeah. So, you know, yeah, the math teacher who can't really count backwards from 10, it's not, don't judge me harshly. Okay, so P of n, this is n times n minus 1 times n minus 2, but it goes all the way down to the last guy, the last one, 3 times 2 times 1. Does anyone recognize that number, what that number is called, what it is?
Is it with the C? Starts with the C?
No. We're getting to that, but we're not there yet.
Oh, okay, never mind.
Is it a factorial?
It's a factorial, right? This is called n factorial. N, right? Not n with it's actually an exclamation point, but it's not. You don't have to shout it. It's called n factorial. It's read n factorial. So the number n factorial comes from this sort of idea. How many ways can I arrange n things in order? N factorial number of ways. N factorial is just a shorthand for this idea. Starting at n, keep subtracting 1 and multiply all the numbers from 1 up to n together, right? So example, P of 5 is called 5 factorial. This is 5 times 4 times 3 times 2 times 1, which is 120. Which, by the way, how many ways can I arrange 5 people in order? 120 ways. You wouldn't want to have to write that out, right? You wouldn't want to have to say, okay, I have David, John, Mary, Adam, Smith. Okay, so I can put David first, then Mary, then Adam, then John, then Smith, or I could put Smith, and you're writing this list out. You would have to write out 120 things. Ain't nobody got time for that, right? You just need to know hey, if I have 5 people, I want to put them in order, it's 5 factorial, number of ways to do that, right? It's 120 ways. I don't want to have to list these all out on an exam, right? So example, the number of ways to line up 5 people in order. So yeah, I'm giving you all these mathematical definitions. Okay, if we have a set with this and how many tuples can we create? But really, there's an application to everything I'm telling you. So that I'm just giving you some examples and telling you what does it all mean? The notation I'm doing, talking about these sets and tuples, what is it I'm actually talking about? If I'm talking about a tuple, I'm talking about an arrangement, right? So if I tell you to count tuples, I'm really telling you how to count arrangements. And that's what you should think about. When you go beyond and we're reading word problems and stuff like that, and we want to count how many things are in certain positions or how many ways I could do something, one of the things you might think about, oh, well, I'd have to arrange things in order to do this, and I can't repeat stuff. And that automatically would tell you I should be thinking of this number, TNM, and I should be using this number in my calculator, right? So, yeah. By convention, there are many reasons why, by convention, for many reasons, we define 0 factorial equals 1. Okay. Now, this has to be true for mathematical as well as conceptual reasons. So someone can say, how many ways can you arrange 0 things? Well, one way, just whatever it is. Like how many ways can you choose 0 people from those 10 people and arrange them in order? Like there's one, I guess. Like there's nothing really that, like, you just don't do anything. That's basically what you're just not going to do the choosing, right? There's only one way to accomplish that. But there are other mathematical reasons why 0 factorial should be thought of as 1, but it is. It doesn't make any sense based on what we are talking about, like, because n is all n as in Nancy is always thought of as a positive number, a positive integer. But yeah, 0 factorial is that. So there's one way to arrange 0 things, right? There's no multiple ways to arrange 0 things. Now some of you might know about permutations, I'm not sure, but this formula might seem very strange to you that this is a permutation. You might know the definition in a more concise form, which I'm going to tell you now that I introduced the factorial. We can rewrite PNM using factorials. So here we have PNM, and we know that this is n times n minus 1 times n minus 2, going all the way down to n, n minus m plus 1. I wanted to write that a little bit more concise. So what we're going to do is we're going to do that sneaky thing that math people do sometimes, and they multiply and divide by the same thing. So it's like they're multiplying by 1, they're not really changing anything. So it's n times n minus 1 times n minus 2, all the way up to n minus m plus 1. And then they continue n minus m, n minus m minus 1, going all the way down to 3 times 2 times 1. They complete the permutation. But you can't just randomly multiply by something, so they divided by that thing as well. So what is the numerator? You'll notice that the numerator is the product of all integers from 1 up to n. That is n factorial. What is the denominator? You'll notice that is the product of all integers from 1 up to n minus m, which means it's n minus m factorial. So our PMN, our PNM is n factorial over n minus m factorial. Or PNR is n factorial over n minus r factorial. But what it really means is to just start at m, keep subtracting 1 and multiply numbers and doing this m times or r times, right? It's exactly the same number as this. Which, if you're doing it by hand, it's probably nicer to do it this way, although you won't be doing it by hand very often. In fact, sometimes I'll have you leave this in your answer, as opposed to actually working out what that number is. Okay, so yeah, that's a permutation. Now, so we know how to count tuples in multiple scenarios. This is useful for arrangements or situations with no repeats. However, sometimes we have no such restriction. So let's figure out how to count the possible number of sets in some scenario. Usually, more specifically, we're talking about subsets, right? So I have a set, and then I want to take elements from that set to create another set, right? So that's what we're going to talk about. As opposed to having a set and I'm taking elements to create a tuple, I'm taking things from a set of things to put them in a certain order. Now, what if it didn't matter what order I put them in? Right? So that's the kind of idea we want to do. So suppose A has n elements. So it's a set. Also assume that n is potentially smaller than n. How many sets of size m, as in mom, can be created from A? What do I mean? Example. If A equals A, B, C, D, E, F, right? And I want to say how many two sets can I create? In other words, I want to choose two things from A in no particular order, right? I just want to put two random things and put them in their own set, right? How many ways can I do that? I have 6 things here in A, and I want to create all possible combinations of 2 things, right? So what can we do? Well, we can do A and B. we can do a, so this is me enumerating. Right, just listing out one possibility, or listing out all possibilities, and I can just count them one by one. Yeah, A and C, A and D, A and E, A and F. Actually, I wanted a little bit less.
Are we using addition here?
Come again?
Are we using addition instead of multiplication? Like we could do 5 plus 4 plus 3 plus 2 plus 1 would give us the amount of sets if you want. Would give us the amount of sets.
No, that would not work.
Okay.
I didn't want that many. I'm going to actually do an example with up to F, but I don't want this example up to F. The example that I'm going to do with up to F is going to be larger. So I want to just write it out with A through D, just so you can see the idea of what I'm heading for. So you can have that. You can also have, what are we missing? B and C, B and D. What else?
I have a question.
Yeah.
Would A and A work out or no?
No,
They both
because
have to
it's
be
a set.
different.
Yeah,
Yeah,
because if you have a set of A and A, that's just the set A.
Mm-hmm.
Because sets ignore repeats.
Got it.
So you wouldn't create that. Yeah, you'd have to pick two different elements. So here you would have, I think C and D is the last one, right? 1, 2, 3, 4, 5, 6. That's all possible different two sets. So here, 6 possibilities. Which is not 4 plus 3 plus 2 plus 1 or anything like that, right? It's not an addition formula. Yeah, so that's an example of what we want to do. Let's make this harder. A equals A, B, C, D, E, F. How many 2 sets can be created? How many 4 sets can be created? Right? So I'm talking about, A, C, E, F, or A, D, B, E, or, right? How many ways out of these 6 things can I pick 4 random things and create another set with them? And you probably realize that you don't want to have to play this game. It's not going to be any fun. Also, you would notice that rearrangements, this is the same as CAEF, which is the same as EFCA. So if you start to do this in some sort of strategy, eventually you're going to realize, damn it, I already have that set. Damn it. And you're going to realize that you're going to have something where you're counting. Because sets, they can rearrange themselves. And you're like, damn it, this is going to be really annoying. So now, so here, let's be a little clever. Here is one such set, A, B, C, D. Now you realize that this guy has multiple representation. Right? For example, I can have A, B, C, D, but that would be the same as B, C, A, D. That would be the same as C, A, B, D. That would be the da-da-da. Okay? Now, to wrap things up a little bit, here's the question. See who's paying attention. How many representations are there? If I were to pick one of these examples and talk about all possible ways that I could write it down, how many ways would that be? For extra credit. I'm kidding, brownie points. Give you guys 10 more seconds because we're already a couple minutes over time. $24. Someone guessed in the chat. Why 24? Right. It is 4 factorial. It is 24. Notice that what I'm doing, to get a different representation, I had to write the letters in a different order. What I was doing, I was rearranging orders. How many possible, so when I ask the question, how many representations I have, it's exactly the same question as how many orders can I write the elements of this set in? 4 factorial, right? I'm just arranging 4 elements to write in a set representation. So for every set of 4 elements, there are 4 factorial corresponding representations. And believe it or not, that actually tells us how to count without counting. What does that mean? This means the number of 4 sets, sets of size 4, is going to be, well, there are going to be more of that thing. So that's going to get multiplied. So for every set, if I want to find out the number of 4 tuples, there will be more 4 tuples than sets, because sets, all rearrangements are counted as 1, whereas with tuples, every rearrangement is counted as different. How many more? There are 4 factorial times more over here. In other words, if I take a number of 4 sets, it's actually going to be the same as the number of 4 tuples divided by 4 factorial. Now, I already told you how to count the number of 4 tuples. This is P of 6, 4. I had 6 elements, and I wanted to pick 4 of them to put in a set. Because my set can be rearranged, I can use the number of rearrangements to count the number of sets in backwards. And so I would have this, right? So that would be the number of sets I can create. And this can be generalized. So if A has n elements, and we want to create all possible M sets, this can be done in P of nm divided by m factorial ways. Now, P of nm over m factorial Well, we know what that is. This is m factorial over n minus m factorial divided by m factorial. And so this is actually n factorial over m factorial times n minus m factorial. This is another important number. So I'm just going to introduce this number and let you guys go. It is denoted C n m. So this is n factorial over m factorial over n minus m factorial, or CNR, n factorial over r factorial n minus r factorial. Sometimes people use k in this position, and it is called a combination. And CNR equals NCR equals NCR equals NCR. There are multiple notations for this as well, but is read. How do you actually say it? Because we always have to sound like we know what we're talking about. N choose R. So finally, CNR is the number of ways to choose R objects from N objects in no particular order. So someone did mention a C earlier. That's the guy. It's the way to count the number of sets that you can create. Yeah, so that's that. We have a little bit more to talk about counting next time. I'll leave you guys with this to do. Make sure you can do this in your calculators. Tell me the answer next time. Tell me the answer tomorrow. C of 25,7 and P of 34,9. And yeah. So that's, guys, called a combination, and that's it for today. So thank you for your time and attention. Have to run to another class now. I'll see you guys tomorrow. We'll do this, do some counting examples, and I'll give you guys your groups. Yeah, enjoy the rest of the day. See you in the next one.